and welcome to the fifth tutorial in this series of tutorials on calculus at the higher level. Now in this tutorial I'm going to speak about the derivative of the trigonometric functions sine x and cosine of x. And my aim here will be to use the graphs of sine x and cosine of x to motivate the expectation for what the derivatives of those functions will be, and then I will just write down what those derivatives are. And then in the next tutorial I'm actually going to derive those derivatives of sine x and cosine of x for you, and we'll be using some of the things we learned in the higher trigonometry tutorials. Namely, we're going to be using definition of radians, we're going to be using the addition formulae that we learned, and again, at the risk of being repetitious, you'll know from watching these tutorials that my philosophy is not just to write things down for you, but to try and show you where things come from, either to prove them, or if proofs are too difficult, to motivate them pretty clearly so that you can feel confident that the things that you're learning are indeed true. So, as I say, the aim today, we're going to look at sine x and cosine of x graphically, use our knowledge of the meaning of the derivative to infer qualitatively what the derivative would look like, and then I'll write down what those derivatives are, and you'll see that that's very consonant with our graphical expectations, and that should give you quite a lot of sort of comfort with those derivatives in terms of plausibility that they're true. And then in the next tutorial I'll prove them for you, which will be quite a satisfactory exercise, I think, because you'll be using exactly those parts of higher mathematics trigonometry that you're learning in parallel, so that should be quite a pleasant thing. And just to remind you that the fundamental formula of calculus that we've been talking about in this series is that a change in the function f is related to the change of the input variable x by the derivative. And we spoke quite a lot about that in earlier tutorials, and we understood this from a graphical perspective, and we understood the derivative of the function f to have a graphical representation as the slope of the tangent to the curve at point x, and we're going to use that understanding right now thinking about sine and cosine. And I will be utilizing radians rather than degrees. That's essential when we're doing calculus with trigonometric functions. That won't be so obvious in this tutorial why we have to use radians, but it will be obvious in the next tutorial when I derive sine and cosine. You'll see that radians enter very naturally into that derivation. Right, so enough talking, let's get down to some maths here. I'm going to first of all sketch sine and cosine, and we're going to use these sketches to do some motivating. So that's going to be my axes for sine, and these will be my axes for cosine as a function of x. And let's see, sine goes between -1 and 1, as does cosine. And we're just going to look at one period of the functions, or one complete cycle. And remember, these functions, just if you know them for one cycle, you'll know them everywhere else, because they just repeat every 2 pi radians, or every 360 degrees, both in the negative and positive directions. They go on forever. Right, so let's label these then. So this is at the end of one complete cycle. We have 2 pi radians, and we have pi radians in the middle there. And let me just, for the sake of it, let me just label these others too, because it's good practice for you to see the equivalent of 90 degrees, the equivalent of 270 degrees, just to get that sort of familiarity with going easily between degrees and radians. Right, so there we are. I sort of set up my sort of axes and pictures for these functions, which call me boring, but I don't know, I just don't get tired of drawing these. It's just I wouldn't say a pleasure, it's not something that I would choose to do if I wasn't doing maths, but it's very satisfying, I think, to draw these amazing functions. Right, so here's the sine of x. Okay, not too bad. And here's the cosine of x. There is something actually about sketching functions. I wobbled there, I apologize, but there's something satisfying about sketching functions in that... Actually, sorry, interrupting myself. Let me just write this. F of x equals sine of x. And on this picture, we're going to be looking at f of x as cosine of x. It just struck me then, sketching these, that by sketching one does actually get quite a lot of intuition about a curve. The fact that there's sort of a parabolic nature to these curves just around their turning points. They're not parabolas, but they have a parabolic form around their turning points. And you really feel that when you're sketching them relatively accurately. You know, and that kind of, I think, aids one's mathematical intuition somewhat. Right, now what I'm going to do is, just as I did looking at, we looked at powers of x, is to just make a rough, I think I called it a Gedanken graph or a Gedanken sketch. It's kind of a daft term really, but sort of a sort of a fuzzy qualitative sketch of what do we expect the derivative to look like. Thinking about the derivative as a function of x and the derivative as the slope of the tangent to the curve f as we vary x. So let me just have make a sketch of that and sort of get a sense of it, okay? And I think you'll hopefully you'll enjoy this, and you'll sort of get a sense of, oh right, that's why these derivatives are what they are. And it's going to be really crude, so I'm not going to be able to say anything about the values on the y-axis. That's too difficult right now. But I will be able to at least talk about the sign of things and their sort of relative size, you know, and that's going to be helpful. Right, so again we have the origin, and what I'm plotting here is f primed for the functions above. Okay, and I've got the same values on the x-axis here. And I'm just going to write them down again because I want you to be very familiar and comfortable with these values of angles in terms of radians, so it doesn't hurt just to keep writing them down. Right, here we go. So let's sort of pick off the easy parts here. Remember, the derivative relates the change in x to the change in f, and wherever I have a curve that essentially has a turning point, then my derivative is very small, and in fact 0 directly at the maximum or minimum. So when I vary x around this maximum here, there is no change in the function. It's exactly around that maximum. The function is constant, sort of in that infinitesimal region. Therefore the derivative would be 0, because we're saying that around this maximum, also around this minimum, changing x does not give any appreciable change in the function. So in the spirit of our sort of Gedanken graphs here, around this maximum we expect the derivative to be kind of around 0, and the same will be true around this minimum. We expect the derivative to be around 0. We can use that immediately over here with cosine. Remembering that these graphs just continue, we can see that cosine here has a maximum at 0, so the derivative should be 0 around there, because again, change in x here doesn't lead to any appreciable change in the function, and we have a minimum of cosine here, so its derivative should be 0 around pi, and again there's a maximum of cosine at 2 pi. So sorry if this has been a bit confusing, but I'm just picking off the kind of the easy bits first. The maxima and minima are places where the derivative of those functions is going to be very small, and in fact 0 at the precise value of x where there is the minimum. So we're expecting the derivative of sine to be 0 at pi over 2 radians and 3 pi over 2 radians. We're expecting the derivative of cosine to be 0 at 0 radians, pi radians, and 2 pi radians. Okay. Now let's see what happens around 0 here for sine. The tangent, if you can sort of imagine, the tangent to the curve there is positive, has a positive slope, quite big, and you see as we go forward in x, that tangent has a slope that gets smaller and it finally goes to 0. So we would be expecting a sort of largish positive value for the derivative here. Namely, again, I'm just going to repeat it, the slope of the tangent to the curve. It remains positive in this whole region because we have a positive slope, but it just gets smaller. So, I'm going to sort of do something crude like that. It then becomes negative. So you see here that the sine function, if we think about drawing a tangent to the curve here, it's actually negative now. It starts off small in magnitude but negative, and by pi becomes a sort of the largest negative value. So at pi it will be a negative slope down here and sort of moderately negative here, moderately negative here, and then goes to 0, and then it becomes positive again, has a small positive value, and at 2 pi has the same slope as it would have at 0, because again, think of these curves just continuing past for the next cycle. So it would be a higher positive value here again for the slope, and something moderate in between. So that's very, very crude what we kind of expect for the derivative of this function, and we're not that bothered about the exact placement of these fuzzy clouds, except we know that these zeros are correct, and we have high positive values, moderate positive values, moderate negative values, and extreme negative value here. And similarly for cosine, let's see, the slope is negative for this entire stretch between 0 radians and pi radians. So if I draw tangents to this cosine curve, you see the tangents have a negative slope for that whole region between 0 and pi, and would have the largest magnitude of slope at pi over 2, but it's always negative. So it would be something like a moderate negative value, moderate negative value, and then it hits 0 here at pi. And then the slope is positive from pi to 2 pi, has a moderate value, a high value, a moderate value, and then goes to 0. So let's see, what did I say? That has a moderate value and it's positive. Here it has its sort of steeper slope and it's positive at 3 pi over 2. And then it gets smaller again, has a moderate value, and then turns over to 0 at 2 pi. And again, so that's our sort of fuzzy Gedanken graph for the derivative of cosine of x. And so you might say, why are we doing this? Why is Thea fiddling around with little green clouds on these graphs? Well, I think it's useful because what you're doing really is that metaphor I've used before of the potter with their clay. You know, we're comfortable with these graphs of sine x and cosine of x. We want to talk about calculus, want to talk about the derivative of these functions, which relates change in x to a change in the function. We know that that can be interpreted as the slope of a tangent. Let's use that conceptual understanding to essentially construct with our hands what we expect these derivatives to look like before we write down some mathematical form for them. Because then when we do write down the mathematical form, it's going to be a familiar thing to us. It's going to be something that we essentially intuitively and conceptually own, rather than a sort of alien imposition on our consciousness, if I might use such a turn of phrase. We can't do any better than this, really. I mean, we could fiddle around more graphically, but this is kind of, as good as we can really do in a reasonable time. I'm going to derive the derivatives for you in the next tutorial, but let me now state what they are, and then you will be able to decide for yourself whether the actual derivatives of sine and cosine written as functions are consonant with these Gedanken graphs. So the derivative of sine of x is beautiful. It's just the cosine of x. Let me just write it here. So if f of x equals sine x, then the derivative is cosine of x. Now, does that make sense? Well, apart from the sort of subtleties of the shape of the function, we clearly see here we have a function in these green clouds that sort of, yes, that could be cosine. It vanishes at pi over 2 and 3 pi over 2, which indeed the cosine function does. It has a minimum at pi, yes, and maxima at 0 and 2 pi, yes. All we've missed really in this kind of crude analysis is really the subtleties of the shape, the kind of parabolic nature near the maximum and minima and so on. But good. So this fact that the derivative of sine x is cosine of x is certainly in tune with, is consonant with the kind of qualitative shape of the derivative that we constructed. And turning to the right side of the page here, if f of x equals cosine of x, then it is a fact that the derivative of that function is the negative of sine of x. So these are the things to take away from this tutorial as facts. Is this consonant with our picture? Well, yes it is, because if we imagine flipping the sine of x, and in fact let me just draw in blue a mirror image of sine x, so minus sine of x would just be flipping this curve about the x-axis. We would have this blue curve here, and if we compare that blue curve with our Gedanken graph here, yes, very good. So zeros at 0 pi and 2 pi, a minimum at pi over 2 and a maximum at 3 pi over 2, very, very good. So again, this fact that the derivative of cosine of x is minus sine of x is in tune with our expectation. Fantastic, and that's all I wanted to achieve in this tutorial. The thing to take from it is the beauty and the simplicity of this result, that the sine curve has a derivative which is the cosine curve. Namely, this cosine curve is actually the derivative of this sine curve. So for any x, the slope of the tangent to the curve sine x is actually given, the value of that slope is given by the cosine of x. So there's a very intimate relationship between these two functions. And likewise, the derivative of the cosine function is minus the sine function. So for any x, the slope of the tangent to the curve is given by this blue dashed line, the negative of sine x. it's amazing how much maths and science is hidden in these rather innocent looking equations. If I was to tell you that a good fraction of all of physics is hidden here, you might not believe me, but it's actually the case, because hidden in here really is essentially the physics of oscillators, which I can talk about maybe in a different playlist of tutorials. There's a lot of mathematics in what's called Fourier analysis hidden in these relationships. Really very, very beautiful. But for now, we just need to accept them as given. And in the next tutorial, I will use, as I mentioned, some of that trigonometry we learned recently about radians and addition formulae to prove them. And hopefully you'll find that quite satisfying. After that, just to give you a bit of a roadmap, I'm going to give a third tutorial in this sort of part of the calculus series on some slightly more formal aspects of calculus. I'm going to introduce you to a different notation, the Leibniz notation, and I will also talk about something called the chain rule, which is an extraordinarily powerful tool in calculus and very straightforward to derive and understand, and we'll be using that a lot going forward. Right, so that's all for now, and I look forward to seeing you in the next tutorial. So bye for now.